So, hi, this is BDT404, large-scale ETL data flows with Data Pipeline and Dataduct. Thank you for coming out to this session. I'm Saurabh. I work as an engineer on the analytics team at Coursera. And today I'll be talking about Dataduct, our in-house ETL framework that was built on top of Data Pipeline, and we open sourced about a year ago. So in this session, I'll be covering how we use Data Pipeline to orchestrate and manage our ETLs, and then why and how we develop Dataduct to develop these ETLs more easily. And like how Dataduct has enabled every developer in our organization to write their own ETLs now, and some of the best practices that we have found in running hundreds of pipelines. And at the end, you should get a very good preview of how you can use Dataduct to write and develop your own ETLs. So let's get started. I'm sure many of you have taken classes on Coursera before or have heard of Coursera, but for people who aren't familiar, Coursera is an online education startup, and our mission is to provide universal access to the world's best education. And to do so, we partner with best universities across the globe, and I'm sure you recognize a lot of the names up here. And we work with them to put their best courses online from the best instructors and then make them accessible to millions of learners. To see the impact of this, let's talk about like some of the scale that we have achieved at Coursera. Currently, we have 15 million learners on our platform, which participate in 1,300 college-level courses. And these courses have been created by 120 of our partners. And all of these courses have been completed 2.5 million times by our learners. And with all this learner activity on our platform, we collect and see a lot of data. And like most companies, our data is stored in like various different source systems in various different formats. And we need to like aggregate all this data into a single warehouse so that our analysts can analyze this data more easily and that we can make it accessible to everyone in the company. For choice of warehouse, we use Amazon Redshift. One, because of like accessibility using SQL. So most of our company was familiar with SQL, so it's very easy for them to like start using the warehouse. And Redshift saw a tremendous performance when we compared it to other warehouse solutions such as Hive. So we ended up choosing Redshift. Currently, of fewer than 200 employees at the company, 167 have written at least one query in the last 1 year. So we're really proud of that fact, because as we strive to become more data-driven as an organization, we want to make data more accessible to everyone in the company. So to get a sense of what ETL at Coursera looks like, let's go through a brief flow of how data is stored at Coursera and how it reaches Redshift, and then how we use that further. So on the left side, you see like 4 primary data sources. So on the top, you have the clickstream data that we collect with our internal eventing system. And this data is then pushed to S3, which is later ETL'd on. And then we run MySQL on Amazon RDS, which works as our relational data store. We also run Cassandra, a NoSQL database. And on EC2, we manage this ourselves. And then we also pull data from some third-party services, such as Facebook, because we have Facebook login available, and then CRM tools if your company uses that, and then support systems, etc. This data is then transformed using either EC2 machines, where you can run a single machine job, or using EMR. And we use Scalding as our framework for writing MapReduce jobs, because most of Coursera's backend is written in Scala. So our developers didn't have to learn a new language when they wanted to write MapReduce jobs. So we could directly use Scala and write our MapReduce jobs using Scalding. Scalding is an open source project by Twitter, for those who aren't familiar. Then we load this data in, then EMR jobs basically push this data into S3, which is then loaded into Redshift using the copy command in Redshift. Now that we have data in a single warehouse and at a single place, we can run BI applications such as Periscope or Looker or Amazon QuickSight once we get access to that, and then use that to make it more accessible and analyze data directly. We also further transform this data to build things like recommendation systems or analyze A/B tests that we have run. And this data is then pushed into RDS or Cassandra based on like latency requirements. So we don't want to serve production traffic out of Redshift. So we load this data into like Cassandra or RDS based on requirements there. So with all this, for all these data sources and us building new features every week, we currently run around 150 active pipelines. So these pipelines run at daily or hourly cadence, and then have been developed by 44 different developers in the company. And to give you a good sense of like what this 44 number means, we currently have a total of 70 developers in our organization. So more than 50% have contributed to ETL in some fashion. So before we start building some of the pipelines, let's talk about some requirements that we have out of our ETL system. So fault tolerance, in case our jobs fail or in case we have a resource failure during running the ETL, so you're running a MapReduce job, one node dies, we want to automatically restart the job and basically not have to go through the whole pipeline again. And we want to and Data Pipeline does an amazing job of providing default retries. So we use that feature. It provides retries on a resource level or at an activity level, which we use here. Then we want the ability to schedule pipelines at different cadence and different frequency at different time of the day. So you can run some pipelines at like 12 in the night, or you might want to run some pipelines at 8 in the morning. And similarly, you have some pipelines that run on a weekly schedule. So if you've received the recommended courses email from Coursera, that runs at a weekly schedule because for like if we are aggregating data from our payment processing system, we try to do that every hour so that we can reconcile our payments. And then other data sources might be okay with like a 1-day latency and similarly. Then instead of having one large pipeline that takes care of all this data, we want different pipelines. So we want dependencies between pipelines. So let's say a recommendation model should not start training before like learner activity data has been loaded. So we want a dependency across different pipelines, and similarly within a pipeline, you don't want your all pipeline to be just one step, because you want that to be more modular, saying extract data and then do some transformation, then maybe do some more transformation and then load that. Then resource management. So every pipeline, let's say it's running a 20-node cluster, and then similarly other pipelines require a 30-node cluster. We don't want all pipelines blocking on single large cluster to run them. So we want some isolation between one pipeline's resources should not be blocked by other pipelines. And similarly, we want some amount of we don't want congestion on a single resource across our pipeline. So every pipeline should start and terminate its own resources and then take care of that. The ability to monitor and alert. So in case you have a job failure or you have like a complete pipeline failure, you want to trigger either a pager duty or an SNS alert around that. The other things you want to monitor is like a health of a pipeline. So how much disk space are you using, or how much data are you processing for a single pipeline is definitely crucial, because let's say you had a pipeline that you wrote a year ago, and that time it was using 50% disk space, but as more user activity comes in, you're reaching that cliff. So you want to get alerted about that in advance rather than seeing the pipeline fail and then you realizing that you've overflown. Then, as we talked about, 50% of the developers in the organization have contributed to ETL, so we definitely want this process to be as seamless as possible. So not everybody needs to know everything that is required to write an ETL. So we want the development environment to be as smooth as possible, and then ability to test these pipelines in dev as easy as possible as well. So Data Pipeline provides all of these features very seamlessly. You can use the web UI to develop your ETLs, but there were some additional things that we wanted to make our development more easy. So we ended up building Data Duct, which basically wraps around the Data Pipeline APIs and makes things more easy to work with. And then some of the features that Data Duct provides are basically code reusability. So we can reuse the same code across different pipelines. So if we were pulling data from the same data source, we don't want to write different pipelines that basically have a replica of that same code. So we want to reuse the same code across different pipelines. And then we want extensibility. So once we develop a new feature, we want the same pipeline framework to be more extendable. So when we initially wrote our ETL framework, we were only pulling data from RDS. So when we wrote Cassandra, we wanted that to be more seamless as well, that we could integrate with Cassandra just like we had integrated with RDS. We wanted a command line interface to manage and develop pipelines more easily. And then I talked about testing. So we want the ability to basically test pipelines in dev before we actually push them to production. And the test environment should basically mimic prod as close as possible. And then dynamic updates is something, let's say we change some source system data model. we don't have to like redeploy the pipeline again. It's like that change should automatically be reflected in the next run of the pipeline. And here we assume that we are testing our pipelines carefully so that once you push in prod, it's like hopefully like guaranteed to work. And then Dataduct is open source. You can definitely find it at like Coursera's GitHub account. And then the documentation is hosted on Read the Docs. I'll put these slides up later, and you can definitely check the link out from SlideShare when these slides are uploaded. The installation is very straightforward. The first thing you only need to do pip install Dataduct and their example pipelines to get you up to speed. So now let's try and build some pipelines to get a feel for what writing pipelines with Dataduct can look like. So the first pipeline we're going to try to write is basically pull data from a relational store and load that into a different into Redshift, which is also relational. So we're going to extract user data from an RDS database and then load that into like a mirror table in Redshift. And this data in this pipeline would be orchestrated by Data Pipeline, and then we basically have an extract step where we'll pull data from RDS and then probably run some transformation if we need to, and then load this into Redshift. So on the left side, you see a YAML file, which is basically our entire pipeline definition. So we say what we're going to parse this out one by one. So in case it's not completely visible, you can reference this later when you have the slides. And on the right side, you basically see a DAG of what the pipeline flow looks like. So these are all the steps that are going to be executed. Some of these steps are automatically inferred based on the pipeline definition, and I'm going to talk about each of these later. So as we saw, the definition of a pipeline is specified as a YAML file. There's a notion of steps, which is basically one action within a single pipeline. And then we're going to talk about other stuff like configuration, overrides, and reuse of code as we parse this pipeline out. So let's talk about steps first. So steps is basically a step is composed of different data pipeline activities. So within data pipeline, an activity is a certain action. And within Dataduct, a step can be one or more of these activities. So if you have a common pattern of like multiple activities that need to be chained in a certain fashion, you can create a step out. And writing a new step is basically extending the current base step class, and then you basically get a new step out. So our first step is basically extract RDS. So we want to extract data from an RDS database. And you specify a SQL query that you want to use to extract this data. So in this case, we will basically get the user ID, name, and email from our users table, and you specify the host name. So the host name is basically which specifies what host it needs to go to. It'll figure out like things like what credentials it needs to use. The credentials are stored as a single config. And then database is basically within that host what database it needs to use. If you specified your query at like userdb.users, you could have just not specified the database name. So this step would basically pull data from RDS and load it into S3. So the next thing that we want to do is now we have all this data that is extracted from an RDS database, and we want to load that into Redshift. So if you know about the copy command in Redshift, it doesn't directly create tables. So you need your table to exist before you can actually start loading data. So create load Redshift is basically just like a generic if statement, so which basically checks if the table has existed or not. If it doesn't exist, it'll basically create the table and then grant permissions based on like how you have defined your user groups. So if you have a developer group, it'll basically grant more insert statements on that, insert permission on that. If you only have a consumer group, then it'll grant like a select access. And then all you need to specify is that this is like the staging Redshift table that we want to load data in, and everything else is like automatically inferred. Then the third step is basically now we have data in the staging table in Redshift, and we want to write this to another schema, which is basically our production schema. Where upsert is basically you update any entries that need to be reflected based on the primary key, and then you insert the remaining statements. So we are loading, in this step, we are basically loading data from a staging table into a production table. Where this helps is like if you have data loaded ETL, where you only load like some time window of data instead of loading the full table, you basically keep your production table as it is, load data into a staging table, and then copy and insert the updated entries into the production table. So these were the three steps that we specified in the YAML file directly. But there were more things that happened in the background when we executed the pipeline. Sorry about that. So the first thing that happened was Bootstrap. So Bootstrap is basically one activity that would run based on what resource you're using. So if you were using an EC2 resource, we would run basically a Bootstrap for an EC2 resource. And if you were running an EMR job, you would basically Bootstrap the EMR cluster. So what happens in the Bootstrap step is like this is automated. So every time you specify a pipeline, it automatically gets the Bootstrap step, where it'll basically fetch the latest binaries of the code that needs to be executed for that pipeline from S3. So every time you change the code in the library, you basically push an updated version to S3. And whenever the pipeline runs next, it'll basically pull the latest version, so which basically enables the dynamic update of pipelines that we talked about. And if you have like dependencies, say you were using some version of Boto and you updated that version. So instead of you having to update the AMI and going across every pipeline, you can basically make your Bootstrap step update your dependencies. This will take some time to, like, if you were installing like libraries that were much more complicated. So that time you can probably, once it takes some amount of time, you can go back and update your AMI, but you don't need to do it every time you install a new dependency. And then it basically makes sure that all your pipelines are running the latest version of code, so you don't run into a stage where some of your pipelines are running like the old code because you forgot to redeploy them, and then some pipelines are running new code, so you only see errors in like half the pipelines, and it's hard to debug. The other thing that happened was when we wrote the upsert step, because the pipeline definition specifies that data is being pulled from an RDS database, we can probably build some amount of sanity checks around our ETL. So the first thing is Redshift does not enforce primary keys, but the primary key, if you specify primary keys, they're used in like query optimization. So you have to manually enforce that your data has primary key, there is no primary key violations. So whenever you do an upsert, it basically checks that your production table didn't have a primary key violation anymore. If it has, it can fire off an SNS alert based on how you configure it. And then you can count the number of rows that you see in your staging table with the number of rows you expected in your source system to basically do that you didn't drop rows between the ETL. And then you can check for corrupted rows by matching data between the source system and your production schema. Where things get slightly tricky is like if you have multiple transformations. So if you had transformations, you can specify that you don't want the you can write your own sanity check instead of using like the default sanity check, which basically assumes that you're mirroring a RDS table into your Redshift. And all this is like automatically done when you specify a upsert step. The next thing that is automatically done is basically tear down. So whenever your pipeline finishes, it will basically run a tear down step. So if you see a failure on your pipeline, you would get an SNS notification saying, hey, this pipeline failed, this was the error message, and that would be fired off. And similarly, it also does logging about your pipeline so that you can monitor, like we talked about monitoring the health of the pipeline. So in this case, you can monitor how many retries do you have, or did like what was like health of the pipeline, saying how much time did your query take, or how much time did each of the steps take. So you can monitor all of this and basically log it into like an RDS database or back into Redshift itself, and then use that to basically build dashboards about your health of your pipeline so that you can catch alerts before like things actually fail. And then we talked about like visualization of the pipeline. So we saw this diagram earlier. This is automatically generated when you specify the YAML file. So if you execute it, you can basically generate the same diagram. And this helps in like debugging data flows and like how your dependencies are specified between steps. And basically the blue boxes here are like actual actions, and then the gray boxes specify like data nodes, which are like intermediate data that is stored in different places in S3. Then you have like a single config. So if you saw that in our pipeline definition, we didn't specify what AMI we wanted to use or what security groups did we want to run this pipeline in. So all this is like stored in a single config that you can override all of these in a pipeline. We'll see that in the next example we talk about. But basically by default, we would use this AMI, what security group do we want to run in, how many retries do we want, what retry delay do we want. All this is like abstracted away from not every developer having to specify these config parameters. Then the other thing is, we talked about extensibility. So custom steps is basically an action where you can either extend upon a currently existing step within the library, or you can build your own steps. When we write our next ETL, which basically pulls data from Cassandra, we'll see how we basically extend upon our existing steps to build new steps out of it. And to deploy this pipeline is very straightforward. All you have to run is basically Data Duct pipeline activate, and then you basically give the path to the YAML file, and it'll automatically schedule that pipeline. There are other options like delaying the pipeline for to start executing in the future, or you want to go back in time and say, I want to start this pipeline like 10 days ago. So all that is specified as a config parameter. So basically your developers have their dev config specified, and then they can just activate the pipeline using a command line interface. So let's jump into a more complex pipeline where we have to actually think about data modeling, and then you have certain more constraints compared to what we saw in RDS. So here we're trying to pull data from Cassandra, which is a NoSQL store, and where we can assume that you're storing blobs such as a JSON object. And then we want to parse this out into multiple tables so that we can create a relational schema out of this JSON object, which can have lists and things like that. And again, this pipeline would be orchestrated using data pipeline. So what our data flow would look like is we'll pull data from Cassandra, we'll push it to S3, then we'll run multiple transformations using EMR. And then once we have tabular data which mimics what individual tables in Redshift is going to look like, we're going to load this up into Redshift. So here we'll talk about basically shell command activity. So shell command activity is a data pipeline action which basically lets you run any command or any shell script. So once we can assume that our EMR cluster has our library installed and a latest version of the jar which specifies the Hadoop job, and then we'll use shell command activity to invoke these. So some of the constraints that we see with a NoSQL store is, one, you're not allowed row scans. So in our previous ETL, we just said select user ID from users table and dump the whole table out. That we don't want to affect production traffic. So if the same cluster is running production traffic, we don't want ETL to basically spike up our latency and destroy the user experience. And so these are one of few of the challenges that you can actually face when you're trying to ETL. So here what we do is basically Netflix has an open source project called Preem, which basically lets you take a backup or a snapshot of your Cassandra cluster. So we would take a backup of our current Cassandra cluster and load this data into S3. And then we're going to use the backups to actually run the ETL instead of actually touching the prod cluster. And then now this backup is stored in a Cassandra specific format, which is called SS tables. So instead of us having to write our own ETL for parsing this SS table format out, there's another open source project which we forked called Augustus. This was also by Netflix, where our version of the fork basically takes in a Cassandra schema. So we specify what schema do we want to parse, and then we would read the SS tables out and then load Avro dumps. So we would basically take every row in Cassandra and create a corresponding Avro row, so that we can work with this more easily instead of us having to learn about the SS table format and aggregating different nodes because they have different versions of the data. Then we're going to use scalding, as we talked about, to parse this Avro files into multiple tables that each look like one of the tables in Redshift. So here we're going to basically build upon the base steps that we specified earlier in our pipeline, and then you convert them into Augustus and scalding steps. So what the pipeline definition here for this pipeline would look like is basically we are pulling data from this votes KVS, which basically has entries for all forum votes. So every time someone upvotes a question or an upvotes an answer or downvotes it, we create an entry in this table. And then we're going to parse this schema out. So we're going to talk about this whole pipeline. So steps, again, we'll talk about the two steps here. So we had a Augustus step and we had a scalding step. So all a developer has to specify for an Augustus step is that he wants to run Augustus, and then he wants this Cassandra schema to be parsed out. And internally, the step definition basically specified where it needs to go for the backups, what date of backups it needs to use based on time of running the pipeline, and then it'll basically create Avro files. And these are basically outputted into an intermediate S3 location, which our next step is going to pick up. So then we have the scalding step. Here, it's going to use the data from the previous step and then run an EMR job. So this, we had a single jar, and then the EMR job is basically specifying a function which basically transformed the JSON object that was loaded in Cassandra into like multiple relational entities. So here you're going to just map over the JSON object and create like different outputs into like different flat files, which each correspond to one of the tables in Redshift. So here we're going to output different nodes. So one, we want to output a different questions table, and we're going to output a different answers table. Now, if you looked at the pipeline carefully, you, instead of us having to specify, like we want to override only certain portions of the config for this pipeline. So we want to change the number of instances that are used by this cluster. So instead of every developer having to number of task node to want to use, number of like what size of the master node is in the cluster, we only want to override certain fields. So here we are only overriding number of instances that we want, number of task instances that we want in our cluster, and the task instance size. And everything else basically falls back to the defaults, which is like EMR roles that we want to use, or SSH keys that you want to specify on that cluster. The next thing we want to talk about is like multiple output nodes. So a single step can basically create multiple outputs that each flow into different following steps. So this scalding step is basically creating two outputs here. One is the questions table, one is the answers table. And then we would use the same old create load Redshift step, which basically takes in data from this questions output node and loads that into like the questions table in Redshift. So we're going to use existing steps that we had already built, and now we have like these two new custom steps, which are like scalding and Augustus, to build our pipeline in like a more modular fashion. We talked about bootstrap, so the same thing would happen again. So this saves like every pipeline definition to having to write this like additional step, because that is automatically inferred. And in case of EMR, what would happen is basically it will fetch the latest jar that we built for our Hadoop jobs. And then one use case before we moved to Redshift was we also had a Hive warehouse. So in this case, you would want like, if you have multiple clusters, you want to talk them, like make them talk to the same metastore. So your bootstrap step can basically configure your cluster to talk to an external metastore. And that way, not every cluster needs to specify like Hive external tables that this S3 location corresponds to this Hive table. So these are some of the use cases of like how you could build like pipelines that bring data into Redshift. So yeah, so we've talked about like bringing all this data into Redshift. So similarly, we could write a scalding step that parses clickstream data, and you could write other like basically poll Facebook for getting data. And now all of your data is in the warehouse. So how can you use your existing ETL framework to build more features that go beyond just pulling data into the warehouse is what we're going to talk about next. So here we're trying to build some data products such as recommendations or dashboards out of our data within Redshift. So what a common pattern pipeline would look like is basically we wait for dependent pipelines. So in case of recommendations, you wait for user activity to be loaded completely. Then we would run some computation inside Redshift if it's possible. So if we can like do all our transformations with SQL, we'll basically run these transformations and create derived tables within Redshift itself. And then you can optionally use EMR or EC2 to process the data further and build like dashboards or recommendation models. And then, as we talked about earlier, you can load back into like MySQL or Cassandra based on latency requirements, and then product features get built on top of these data sources. So to walk you through an example, let's talk about recommendations. Yeah. So recommendations. So here we want to like bring our objective is basically taking a learner and bringing them to the right content. So every time a learner comes to our website, we want to recommend them relevant courses based on their past behavior, based on their past courses they have taken, enrolled in, or courses they have completed, or course pages they have visited to get a sense of like interest based on their previous search queries. The products we can build out of it is basically recommendations email. So you can send a weekly email saying, hey, these are few courses that we think you might be interested in, and then you can have a course discovery experience where every time someone searches on your platform, you basically personalize that search based on their past activity. And then you can use this to reactivate old users who haven't been on your platform by sending them relevant information about your current courses that might have updated or changed. So how our pipeline looks like currently is basically let's assume we are building a simple recommendations model based on enrollments. So we have enrollment data of per course per user entry in our Redshift database, and then we run some computation to calculate a co-enrollment matrix, which is basically an specification of interest of people who are interested in course A, how likely are they to be interested in course B. We run an EMR job, which you can either specify if you were using Spark, you can use MLlib. We wrote it in Scalding. There are other machine learning options that you could use to train your model. Then you basically push this model file into S3. So now, and then the prediction API layer, which the backend server can basically continuously monitor this file every time you update the model. It basically starts using the newer model to create predictions. So the contract between our prediction server and the offline training job is basically specified by this model file till the time it's in the same format. So this is similar to what the contract between a front end and a backend server is. So you basically, till the time it's in a certain JSON object format, the front end and back end can talk to each other. Similarly, you can say your training pipeline and your prediction service basically talk via this model layer. And now, instead of just doing ETL with our job flow manager, we basically extended it to do more complex things. And so this is one example which we currently use our ETL framework for. The other big use case internally we have, So one use case could be internal dashboards. So you have key performance indicators about your different teams in the company. You have different goals, different metrics that each of the teams are optimizing on. You have company level goals such as revenue or user growth that you want to monitor and make them accessible to everyone in the company. So instead of everybody writing SQL on your data warehouse, you can build dashboards on top of it. You could build dashboards directly using a third-party tool like Looker, but if you have more complex transformations that cannot directly be specified using a SQL query, you want to basically do more transformations to calculate these metrics, load them back into MySQL, and then basically have an API layer on this MySQL database. So our objective here for building dashboards would be we want to make data more accessible. Use cases can be results from an A/B test experiments that depend on clickstream data, other metrics that come from different data sources, all of them being computed and loaded into MySQL. And then we basically build a thin API layer which basically fetches the data and renders it. So this dashboard basically shows number of page views about that dashboard itself. And we basically render this. These are some of the example cases. So we talked about 2 ETLs that we pull data into Redshift, and then some examples of how you can use this data. So now I want to leave you with some of the learnings that we have derived in running and managing all these ETL pipelines. So first thing is you should always focus on monitoring things that are not just failures about your pipeline or failures between different actions. There are other things that you can monitor, such as runtime of your pipeline, number of retries that you ran into, number of times this pipeline has been deployed, so in case you have issues with failures, and then query time. So how long does it take for you to load data back into Redshift, and if you see a 2x, if your time doubles in a single day, you want to probably notice those cases as well. Originally, when we started writing ETL, a lot of our ETL code used to live in scripts, and moving that, and then we would have the copy of the same script running across different pipelines, which made it very hard to update, because every time you had to update a single script, you would have to redeploy all of these 5 pipelines. So moving code back into libraries instead of scripts, and keeping the script as thin as possible so that you can dynamically update your pipelines without having to redeploy each of them. So only time we try to deploy a pipeline is when the flow of the data changes, and not just some logic within a single step changing. Then you should have your test environment be as close to prod as possible. So in our case, we run like a smaller Redshift cluster, which basically is only used for testing pipelines. So we use the same backups or read replicas when you run a pipeline and test, and just change the S3 path of what like intermediate nodes to store data in, and then configs and credentials are updated based on what config you run the pipeline with, and then it gets loaded into a smaller Redshift cluster. And then having like a single library or framework to write ETL so that you can get every developer to write their own ETL. So every time a new product feature is launched, we don't have to wait for the ETL to be created like a month. Like writing the ETL should be as seamless as possible so that we can get data access to this data as fast as possible. And then there are things like using backups, which you can do for like NoSQL stores that make writing ETL much more easily, and keeping in mind that you don't want to affect production traffic while you're writing your ETLs is definitely a good important thing. Some of the things that I would avoid would be having large scripts. So one script specifying 10 different actions for a single pipeline. So every time you have a retry, you basically go back to the whole script and do the whole processing. These things should be avoided. And then non-version control pipelines. So even if you have a web UI layer, having audit logs about every time your pipeline changed. You want to notice that if someone is on call, they can basically look up whatever changed within pipelines as fast as possible. And then having really huge pipelines. So if we had built a recommendations pipeline saying user activity is first half of the pipeline and the recommendations model is the second half, that would have been much harder to maintain than saying user activity is one pipeline and then recommendations is another pipeline, and we just have like dependencies across different pipelines. So one cheap way of doing dependencies, even if you don't have like explicit dependencies specified, is having like a time buffer between them. So you want like a single pipeline to be in charge of like only one thing rather than doing multiple things across different different areas of jobs. And then there's some things that generally people don't catch, which is like your query times increasing or having delays in a single pipeline based on due to different issues. So catching those is also important because that can be a trend setter for like if your query times are increasing continuously, then you want to like do something about it before you actually see a failure. So in this presentation, we talked about like how we like create a reusable, extensible experience with Data Duct, the command line interface, and having a good staging environment makes writing ETL much more easier and friendly to developers. And then how dynamic updates basically save us from like having to deploy all pipelines like multiple times in the day. And then it is open source, so feel free to contribute using creating issues, pull requests, and then general guidance how we can improve the project. The documentation is available, and installation is very straightforward. There are around 15 examples in the documentation, which you can get started with, and then feel free to reach out on GitHub for any issues or comments that you might have. And now I can take some questions. We also have Steve from the Data Pipeline team who can answer some questions about the product as well.